This recording will be over the first part of chapter 20. The whole chapter is about carboxylic acids and nitriles, and we're going to start out by talking about the carboxylic acids, and then later in a different section we'll talk about nitriles. And so we'll start with the nomenclature. The nomenclature of carboxylic acids is going to require us to take the alkane name and drop the final E and put in the word oic, skip a space, and then the word acid. And because the carboxylic acid is the highest oxidation level for carbon, except for CO2, then it is the highest priority group that we've studied. And so it will take priority, plus the fact that the carboxylic acid has to be at the end of the chain. So it's going to be carbon number 1. And so that's going to dictate how the other things that might appear in the chain get named, including even aldehydes or other carboxylic acid derivatives and ketones and alcohols, alkenes. None of those things are going to dictate the name over the carboxylic acid groups. So here's a few examples that were in the book, and you can see the numbering system. It's pretty straightforward, and here's even an example with 2 carboxylic acids in it, and so they use the di as a prefix in there, dioic acid. You notice there's nowhere in here is there a number 1 to tell you that the carboxylic acid is on carbon number 1, because we know that. Occasionally you'll see a carboxylic acid that's part of a larger molecule that it can't be numbered in sequentially in the chain. So in the case of this ring, we let the carboxylic acid group be attached to carbon number 1 of the ring, and then we use the word carboxylic acid tacked on to the rest of the name of the ring. And we might also remember benzoic acid from the aromatics chapter, and so benzene carboxylic acid is actually the proper IUPAC name for dealing with that. But we call it benzoic acid, and there's plenty of other common names that are used for carboxylic acids because they're important biological compounds, and sometimes the names are based on where the acid was first isolated. For example, formic acid is the name for the common name for the 1 carbon acid, which you might call methanoic acid in IUPAC. It's called formic acid, and it comes from the ant family, Formicidae, and oxalic acid is a dicarboxylic acid of 2 carbons, which would be ethane dioic acid if you were doing IUPAC, and it comes from the oxalis plant. And so here's this table that's in your book, and it has a list of the common names, and you should familiarize yourself with these common names. Now you notice that the first set of them are just have 1 carboxylic acid, and then we have a group of guys going down to here that have 2 carboxylic acid functional groups. Total number of carbons is dictated by these names. And then there's a few others like this one. We've run across some related molecules to this. Acrylic acid and maleic acid and fumaric acid is the trans version. We've run across some of these before in other chapters, but so here they're all put together. And glycolic acid, obviously that's important biologically. So you should know these names, and here's a few others that are continuing on that same table. And I mentioned benzoic acid, and so this is a common name for the benzene carboxylic acid. And phthalic acid is the ortho dicarboxylic acid on the benzene ring. And there are other common names, but these are the ones that you need to know. And obviously lactic acid, some of these others you'll recognize as being important biologically. Now these carboxylic acids have fairly high boiling points, and if you look at a family of molecules and compare boiling points, maybe you might want to do it on the basis of the molecular weight. So ethanol's molecular weight and formic acid's molecular weight are about the same, but look at how different their boiling points are. Or you could do the same thing with propanol and acetic acid, and again, same molecular weight, but really much higher boiling point for the carboxylic acid. And so the obvious question is, why, when they have the same molecular weight, do they have such different boiling points? And so the answer lies in hydrogen bonding. Because these things can hydrogen bond and make essentially a dimer. And the way this is drawn, you see a hydrogen bond is actually linear, and so there's two of them, and if you actually count, this is an 8-membered ring if these were all real bonds. And those are fairly unusual, but because of being able to make two hydrogen bonds at once, this is actually very favorable. And one of the things it says to us is that these hydrogens at one moment could belong to this oxygen, and the other moment this hydrogen could belong to this oxygen, and this electrons could move around and the double bond would be here, and then this hydrogen would belong to that oxygen. In other words, you can't really pin down which molecule the hydrogens belong to at any given time, and that's part of what caused the broad peak in the IR when we were looking at carboxylic acid OH bonds in the IR, and how they got really broad if you had a sample that was concentrated or neat and there was no solvent to dilute the carboxylic acids, then you get these really strong hydrogen bonding features. And besides the fact that you can't really tell who the hydrogen belongs to, you also see that I can't really tell the difference between the oxygens, because at the moment that this one gives up this hydrogen, it becomes a double bond, and this one becomes a single bond when it gets that hydrogen. And so you can't, not only can you not tell which molecule the hydrogen belongs to, you also can't tell the difference between those two oxygens. And these are called carboxylic acids because they are acidic. Not compared to mineral acids so much. If you look at the typical pKa's of mineral acids, they're less than 1. But if you compare these guys to other organic compounds, they're relatively strong acids. And the pKa's we'll look at in a second, but there's an OH bond, and because that's a very polar bond, it's pretty easy for them to ionize. And also because when they ionize, then you have resonance stabilization of the anion. And again, you can't really tell the difference between these two oxygens because at any given moment, either one has negative character. And you know how resonance works. Really, both of them have negative character, and the electrons are shared between these three atoms. So here's our table of pKa's, and there's a couple of tables here we'll look at. This one is carboxylic acids that are basically based on carbon chains, some with double bonds, some without, and this one actually has a ring in it. But we're looking at kind of a trend here, and if we say, a lot of times people like to use acetic acid as kind of the foundation molecule here because it's so common. And it has a pK of 4.76. So, you know, if we were just going to ballpark it and say a typical carboxylic acid has a pK, we'll round it off and say of about 5. So what we see in the way of trends here is that if we put more electronegative stuff nearby, even just a double bond or the aromatic ring, another oxygen, those things make it get more acidic. And actually, just a plain hydrogen and no extra carbon makes it even more acidic. And if we load it up with a bunch of halogens, like in trifluoroacetic acid, it's really quite acidic. Not quite as much as a mineral acid like HCl, but it's getting significantly more acidic. Whereas if we put more carbon around it, in this case, they just have one example, but adding another carbon makes it a little less acidic. And if they had put in here with 3 methyl groups around here instead of these 3 hydrogens, it would be even a little closer to 5. And then they put ethanol on there for comparison's sake. Ethanol, remember, alcohols are similar to that of water, so the OH bond is significantly more acidic in these carboxylic acids than it is in alcohols, and we attribute that to the resonance stabilization of the anion. So to summarize to a certain extent, we can say that if you put more electronegative elements near the carboxylic acid, then that pulls electron density away, and thereby makes it easier for the proton to pop off. So that weakens the proton to oxygen bond. And so because it's easier to ionize, that's going to make it a stronger acid. For example, the trifluoroacetic acid was a pretty strong acid. And you can observe this even easier if you look at substituted benzoic acids. And we talked about some of those trends of electron withdrawing, electron donating characteristics when we talked about electrophilic aromatic substitution. And actually some of our ideas about those properties of the various groups were based on their effect on the acidity of benzoic acid. So here we have another table. So if we look at this Y group, as we make changes to this Y group and then check the pKa of the carboxylic acid group, remember how the pKa goes. As we get to smaller pKa's, that means that we're getting weaker acids and larger, smaller pKa's. Let's get in the right column. We get smaller pKa's, then we're getting more acidic, and consequently the conjugate base is getting weaker, and the acid's getting stronger. Or we can go the other way, and so all of these are in the range. Remember, I said the typical thing is around 5-ish, so we're kind of all in that ballpark, but we see these trends. And remember, these things are color-coded to match up with the color coding in the aromatics chapter. When we looked at electron donating groups were blue, and the best electron donating groups were ammonia or nitrogen NH2 groups, and then OH groups. And there were those guys that had pairs of electrons that could donate into the ring. And then alkyl groups were slightly electron donating, and then just plain benzene, which would represent with this hydrogen here. So plain benzoic acid's about 4.19. We had the halogens, which were electron withdrawing, but also orthoparadirectors, and so their electronegativity wins out, and that's why the dipole moment was toward the halogen, and so they're a little bit more acidic. And then we had those groups which were in resonance. You put in conjugation an electronegative element out there in conjugation with the ring, and that pulls electron density even more. So those were the most electron withdrawing. Well, they're pulling electron density away, making this OH bond even weaker, and so your strongest acids are the ones that are best able to pull electron density away. And so you see these trends. Again, you're not seeing a huge difference in overall in the pK, but you're seeing a trend, and we're interested in that trend. So you should be able to look at several different carboxylic acids and pick out which one would be the most or the least acidic based on this kind of information. Alright, so we're talking about carboxylic acids. They do react with bases, and our typical favorite base is sodium hydroxide, and a carboxylic acid will react with sodium hydroxide and make a salt. It's a very obvious kind of thing to do, and that should be a plus sign, not a little asterisk. And this is the basis for separating and purifying and sometimes titrating to find molecular weights, is to use a reaction as simple as this. So we can extract carboxylic acids into aqueous solution by using aqueous sodium hydroxide solution, and then once you've got it separated, then you can reacidify it. Or if you know the concentration of the base that you're titrating with, and you know the mass of the carboxylic acid, then you can calculate the molecular weight once you know how many milliliters of the base it took to neutralize the solution, and that's how you find the molecular weight. So we've taken advantage of all these kinds of properties of the carboxylic acids along the way, perhaps in lab. And there's, how you do the calculation to find the molecular weight. So that's the end of the properties and nomenclature portion of this chapter.